In this video, we're going to talk about root locus for control systems. We'll define what root locus is and what we get from it. Before I totally start into that, I want to try to clarify some terminology. Say this is our basic feedback system. We've got a forward path gain G and a feedback gain H. In fact, those are the definitions. Everything in this forward path, even if it were multiple blocks, product of everything up here is the forward path transfer function. Here it's just G. And just ignore this disturbance input for this little bit. The feedback, everything in this feedback path, the product of everything in this feedback path, that is the feedback transfer function. The product of both those guys, or all those guys, is called the loop transfer function. And if you want the end-to-end from input R to output Y, you need to do this calculation. This good old G over 1 plus GH. You should have memorized by now if you've gotten this far. And that is the closed loop transfer. The characteristic equation from here is 1 plus GH. We're going to want to get that into this form, because L of S, this L of S is where root locus starts. And we require that this L of S have monic numerator and monic denominator, where monic means the coefficient of the highest power of S is 1. And then K will be the root locus K. I'll explain that in a couple seconds. I want to talk about this L of S just for one chart anyway. Oftentimes, this top bullet, if this is your basic thing, that what you're interested in is some gain up in this forward path. And if G and H are already monic, then that L just is the product of G and H, or it's the loop gain without the K in it. Many problems will be like this first bullet. It'll be handed to you, and then you will do root locus by hand. Talk about that later as well. If the parameter of interest is some gain in the forward path, if G and H, or G times H is not monic, numerator and denominator are not monic, then that L is just some constant times G and H, G times H. And K just is whatever it takes to make this L monic, numerator and denominator. And the root locus K will just have to absorb that K. You'll see this second bullet in the next couple of charts. If that's not true, if the parameter of interest is not just some gain in the forward path, then we've got work to do, and I'm saving that for another video. So let's get to what root locus is. Here's the whole definition, at least as far as I'm concerned. It's the path of the roots of the closed loop characteristic equation traced out in the S-plane as a system parameter varies from 0 to infinity. What are the roots of the closed loop characteristic equation? They are the poles of the system. Remember, pole placement is a big indicator of the behavior of the system, especially the dominant poles. Remember, we did all that before. So let's say you had this. You had a gain in the forward path in this little plant here, and you want to know, how do the poles of the whole closed loop system vary as I increase K from 0 to infinity? Case of P. Here's the characteristic equation. One way to write it with this ratio in it. And I want that to equal this thing. with this K times an L of S, where this L has monic numerator and denominator. Well, if I make K equal to 6K sub P, this part's monic, right? So my root locus K is 6K sub P. K sub P is really my parameter of real interest. And the L of S is this part. Root locus of this is going to show how the closed loop poles vary as this K goes from 0 to infinity. To get back the parameter of interest, I need to divide this K by 6. Okay. Do another example. Here you have a K in the forward path. That's one of the easier cases. But G and H aren't monic for one reason due to this 200, and for another reason due to this 0.25. Here's the loop transfer function, which means all this stuff multiplied together. This. I make K prime equal to 800K, where K is the parameter of interest here. And this would be my L, and it's monic numerator and monic denominator. K prime here is going to be the root locus K. And here's the characteristic equation. Here's the denominator. Well, this isn't the characteristic equation. This is the closed loop transfer function. But here's what we need. So we have a L of S as monic numerator and denominator, a root locus K, K prime, which is 800 times K, which was the original parameter of interest. Now let's see, what does a root locus look like? Here it is when generated by MATLAB. The X's are where the poles of L are. If L of S had zeros, we put little O's there, X's and O's. This particular L, here's the L, it didn't have any zeros, so there's no O's to put here. As K starts at 0, the closed loop poles, remember, these X's are the poles of L of S, not the closed loop poles. In fact, the idea is, where are the closed loop poles without having to do the whole closed loop analysis? When that K prime, the root locus K is 0, the closed loop poles are exactly at the poles of L of S. As this K prime increases, closed loop poles move along these colored lines. And watch what we learn. So it starts out, here's your dominant pole, and here's your two dominant poles, two real poles, or two poles on the real axis. So it's going to start out acting like an overdamped second order system. Guys, a little bit further to the left, right? Then as this K prime increases, this pole starts moving that way, this pole starts moving that way, closed loop poles, and this guy starts moving left. So you still have something that acts more and more like an overdamped system because this guy moves further left up until the point where these two poles meet in the middle, or roughly in the middle. And at the point they meet, you have a double pole at that location. That's where it acts like a critically damped second order system. And then as K prime gets even bigger, these poles move off the real axis. So you'll have a complex pair of poles. You start getting oscillation and overshoot. it starts acting like an underdamped second order system. This guy keeps moving further left, so it becomes less and less relevant to how these two dominant poles work. And then as K keeps getting bigger, at some point you get to where they go through the imaginary axis. At that point, you have sustained oscillation. And as K prime gets even bigger, these poles move into the right half plane and you have an unstable system. Look how much we learned from the root locus graph. That's a lot to know about. And that's what root locus does for you. Here's the same graph, and all these bullet points are what I just went over. I'll save this parameter of interest analysis for the next video. So that's what root locus is. It's a graph that looks something like this. Where are the closed loop poles as you change some gain, or some gain goes from 0 to infinity? And we're also going to learn how to do this by hand. That's an introduction to root locus.